Y van a decir que lo mejor es utilizar...
Poniendo la grabación.
Sí, ya me salió el...
Porque este último al final. Yo esto es como arcano, un rumor. Yo he oído un rumor antes de... La información tiene que fluir mejor en algunos temas.
Esperar un minutillo más. Voy a ver si Café bien.
Pues yo solo sé ese email tan tenebroso que mandó. Exacto. Pero vamos, yo lo dije y en ese momento arrepentí, pero ahora ya no me arrepiento. Nadie ha perdido dinero apostando en contra. Así que no me he preguntado, o sea, tampoco, casi nada tampoco.
Okay, thank you very much for being here. Today we have a special guest, Idaira Yanes Rizo. She's from ICO, del Opino, from Tenerife, and is finishing the PhD with Manu Torres in the measure of black hole masses in quiescent X-ray transients. She did the degree in Madrid and the master in the Canaries, just to go outside of the island for a while. And today she's going to talk us about the measurement of black hole masses in X-ray transients. So whenever you want, it's all yours.
Thank you so much for the presentation. So hello everyone, and welcome to this talk titled Black Hole Masses for Faint Quiescent X-ray Transient. I am Idaira Yanes. I am a PhD student at ISC, as Juan told you. And first of all, I would like to apologize because those days I've got a cold. So if you don't understand something along this talk, feel free to interrupt me whenever you want. Well, I think everyone here knows what a black hole is, but is not very familiar maybe with the words quiescent or X-ray transient. But not worry, don't leave the room. I will try to introduce to you to this exciting topic. In this talk, we will go through a brief introduction of what an X-ray transient is and how we can detect and study them. I will explain two different techniques to obtain the orbital parameters in this system, the classical dynamical method and the novel empirical calibration set for a sample of well-known X-ray transient. I will present two practical cases where we derive the masses of the compact object for the X-ray transient XTE J1859+226 and the historical transient Idaira by employing these two methods. Next, I will talk about a new exciting project that will be carried out there at the Javalambre Observatory for detecting new quiescent black hole X-ray transients. And finally, I will end with some conclusions. So, okay, let's get started with the real fun. My work is purely an observational project with the main goal of improvement and increasing the statistics in the black hole masses distribution in our galaxy. I here present the observational neutron star in X-ray binaries and the stellar black hole masses spectrum known until the date. We can observe that the uncertainties in the black hole masses are pretty significant compared with the neutron star. Kind of my job is trying to reduce these error bars for some of the black hole masses. As we will see, these error bars are dominated due to the huge uncertainties we usually have on the orbital inclination for this system. Refining this distribution is a key problem, for example, to establish tighter constraints on their formation models, as it can be compared with those predicted from different supernova models. But the first step is how we can detect these galactic black holes. As we all know, these bodies, if they are isolated, they are pretty hard to find. However, if they interact with their environment, it can be easy to catch them. For example, if they accrete matter from a companion star that is orbiting around, I have to warn you that this object is going to take a photo of you now. And the interaction between these two bodies originates phenomena that are detectable by our instruments. This binary system is what we call an X-ray transient, where the compact object can be a neutron star or a black hole. I am interested in the system where the compact object is a black hole. The black hole X-ray transients are binary systems containing a black hole accreting matter from a low-mass companion star via an accretion disk. These transients are firstly discovered when they brighten suddenly, as we are seeing in the animation during an outburst episode. This event is caused by mass transfer instabilities in the accretion disk that typically last a few months to about 1 year. These episodes are unpredictable, and during this event, the optical light is fully dominated exclusively by the accretion disk contribution. However, these X-ray transients spend most of their time in a low luminosity quiescent state, when their optical emission is frequently includes a significant contribution from the companion star. This provides the best opportunity to analyze the orbital motion around the compact object and obtain dynamical information that eventually will allow us to estimate the masses of the black hole, which, remember, is our main goal. As I mentioned before, refining the black hole masses distribution in our galaxy is essential to test, for example, the observational models of these stellar remnants and their pathways. But this is not the only reason why studying these systems are important. Due to the proximity at which these objects are located in our galaxy, and due to the fact that these systems undergo accretion processes during the outburst and quiescent state that last a human timescale, that make it easier to study them. They provide a perfect window to study phenomena involving accretion, gamma ray and X-ray procedures during these two states. And the black hole masses distribution can also serve as a reference sample for studies of gravitational wave sources. Stellar evolution theories predict millions of these stellar remnants in our galaxy. However, as we will see later in this talk, we have not been able to detect more than 70. What are the others? Is it an instrumental limitation, or there is a problem with the current theories? Increasing and refining these statistics will help to solve this mystery. And how we obtain the masses? The masses of the components of a binary system can be derived following the Kepler's law. The resulting equations are shown here in the slide. And these values depend on the binary fundamental parameters, such as the orbital period, the radial velocity semi-amplitude of the donor star, the mass ratio, and the orbital inclination. As I mentioned before, one of the most difficult orbital parameters to measure is the orbital inclination. But even without knowing this value, there is a way to determine whether the compact object in an X-ray transient is a neutron star or a black hole. We can set a solid lower limit to the mass of the accreting star by considering the string case where the binary is in H-on, meaning a 19-degree inclination, and neglecting the mass of the companion star. This is what we call the mass function. If this parameter exceeds the 3 solar mass limit, we say we have proven a dynamical black hole. So in summary, for obtaining the black hole mass, the only job we need to do is to measure these 4 fundamental parameters: the mass ratio, the orbital period, the radial velocity semi-amplitude of the donor star, and the orbital inclination. Note that these values are related to the orbital motion of the companion star. And when we were able to detect this component, well, exactly, during the quiescent state. It is during this long-term, low luminosity episode when the stellar component may be visible and be able to trace its motion around the compact object. We perform dynamical studies of X-ray transient in this state where the combination of time-resolved photometry and spectroscopy lead us to the black hole mass. Nowadays, we have two different approaches that can be used to estimate these orbital parameters, and I will start with the classical dynamical method. Here I present the example of the spectroscopy study made for the X-ray transient EA Aquarius. Here we can see the trail normalized spectrum where the vertical axis here is the time evolution. These are a huge number of spectrum taken during 4 nights. The white horizontal line is the separation between those nights. The white traces are the absorption features associated with the stellar component of the binary. This is the perfect example to observe how the absorption lines trace the orbital motion of the star around the black hole. This stellar detection provides the best opportunity to measure the radial velocity curve via cross-correlation with the spectral templates from this Doppler motion. And that's how by fitting a sinusoidal model to the curve, we were able to obtain the orbital period and the radial velocity semi-amplitude of the donor star. With the optical spectroscopy, we are also able to estimate the mass ratio of the system by resolving the rotational broadening of the absorption line from the companion star by subtracting the stellar template. From bottom to top, here it is presented the normalized spectrum of a K0 template. The same spectrum is shown in the second line, but it is optimally broadened to reproduce the line observed in the target. Here is the normalized spectrum of the X-ray transient B404, where we can see that in comparison with the spectral template, the lines are broader. So we need to broaden our spectral template. And finally, here is the residual after subtracting this spectral template to the normalized spectrum of our target. We can observe that by subtracting this spectral template, we can calculate the mass ratio here. This relation, by using this relation is obtained under the assumption that the orbit of the system is circular. The angular momentum vector of both the orbit and the companion star is aligned, and their rotation is synchronized as a result of tidal interactions. Knowing the radial velocity semi-amplitude obtained by the radial velocity curve and the projected rotational broadening, we can derive the mass ratio of the system. As we have seen, optical spectroscopy help us to estimate 3 orbital parameters. On the other hand, time-resolved photometry yield a modulation in the light curve due to changes of aspect of the surface of the companion star projected on the sky. This is what we call the ellipsoidal variation. On the screen, we are seeing the R-band light curve obtained for the X-ray transient XTE J1859+226, where we can see two maximum at phases 0.25 and 0.75, and two minima at phases 0 and 0.5. To help with the visualization of these phases, this is what we are seeing, the position of the companion star in each of these 4 phases. From the light curve, we are able to obtain the orbital period of the system by computing a periodogram, for example. This is the same method of deriving it by the radial velocity curve. In addition, we can model this light curve to obtain the orbital inclination. However, this inclination is also strongly dependent on the accretion disk contribution to the total optical light, which unfortunately the quiescent accretion disk in this black hole vary on a night-to-night basis. These are the light curves obtained for an X-ray transient during quiescent in three different features. And although the morphology of the light curve is stable, we can differentiate three different states: a passive, a loop, and an active state of the accretion disk. The ellipsoidal modulation is an ideal case where in the real practice most of the light curves are affected of what we call flickering activity. This is the one that we are seeing here. They are strong short-term aperiodic variabilities that is affecting the amplitudes of the light curve, which this effect can skew the determination of the orbital inclination and thus the mass measurement of the black hole. And this is why the uncertainties of the orbital inclination is the main problem to the black hole masses. So we have seen how the combination of photometry and spectroscopy lead us to obtain the black hole masses. Although it seems like a simple task, the reality is that between the 70 discovered X-ray transients, we only have dynamically confirmed 19. Here I show you the histogram of the black hole candidates discovered since the start of the X-ray astronomy area. And also the red bars represent the black hole candidates, and the green the dynamically confirmed one. The start of operation of ground-based telescope between 4 and 10 meters are marked in the figure, and we can see that the start of the GTC in 2008 we didn't recover a lot of dynamically confirmed black holes. The remaining 50 unconfirmed black holes, after their outburst episode, they become too faint for dynamical studies, even for the 10-meter telescope. At this point, we needed new methods to reach for those black holes. During this talk, I made you believe that during quiescent, the companion star is easily detected, but unfortunately, this is not an usual case. In many cases, it is not visible because it's too faint, they are a low mass companion star, or there is a lot of a strong contribution of the accretion disk, which was the flickering activity I mentioned before. However, this binary system have a very important and interesting spectroscopy feature. They present a double peak H-alpha emission line as a consequence of the orbital velocities distribution of the gas in the accretion disk. Exploiting the properties of this line by employing the orbital information published in the literature of the well-known X-ray transients, had led us to derive empirical correlations with the fundamental orbital parameters. The first empirical relation correlates the full width at half maximum of the H-alpha emission line with the radial velocity semi-amplitude of the donor star by following this linear equation. In the left picture, it is shown the H-alpha emission line of some of the X-ray transient used for the calibration. And this method consists of fitting a single Gaussian to the individual spectrum. This is a robust way to parameterize the line width. In the right panel, it is represented the linear fit to the individual values of this sample of X-ray transients. And this relation is also well established for the near infrared regime by plotting not the H-alpha line, but the helium-1 emission line. in another sample of dynamical black hole X-ray transients. The resulting equation is very consistent with the one obtained in the optical. And the similarity between these two correlations seems to imply that the width of the H alpha and the near infrared lines are consistent during quiescent. Another important relation is the one that directly correlates the mass ratio of the system with the double peak separation and the full width of maximum of the H alpha emission line. In this case, a double symmetric Gaussian is fitted to a sample of the well-known X-ray transient, and the best linear fit in logarithm scale is also plotted in the right panel. To obtain a good measurement of the X-ray of the mass ratio, it's necessary to estimate the separation and the double peak separation and the full width of maximum with very high precision. Otherwise, we will have large uncertainties on this orbital parameter. So being able to detect the double peak H alpha emission line allow us to derive the mass ratio and the radial velocity semi-amplitude of the donor star. But it doesn't stop here. Yeah, I know. We are draining this line like a PhD student as we can. And one of the most important relations have been recently published. These relate the depth of the throw of the H alpha emission line with orbital inclination, following this linear equation. A two-symmetric Gaussian fit would deliver the orbital inclination of the system. We can see that this depth increases with the inclination, as we are plotting here with the best linear fit. The morphology of the emission line suffers from orbital and systematic variability. The depth of the throw is very sensitive to these changes. So, which means that in order to use this relation, we need to have a good phase coverage of the orbital motion of the star. At least more than 50% of the orbit we need to be covered in our spectrum. So, in summary, we have different techniques to obtain the fundamental parameters in X-ray transient. We can perform dynamical studies. If we are able to detect the companion star, we can obtain the radial velocity semi-amplitude of the donor star, the orbital period, and the mass ratio. And if we have an ellipsoidal modulation, we can estimate the orbital period and the orbital inclination. In the cases where the companion star is not visible, we can use the empirical calibrations with the H alpha emission line to obtain the three orbital parameters. So now that we have all these techniques, let's see how we apply them in a real case. In my thesis, I work with the historical X-ray transient Kytra, which was discovered in 1974 by the Ariel satellite, but no dynamical studies have been published until this work. The X-ray properties displayed during the outburst episode suggest the presence of a black hole in this transient. Before our work, there was a photometric and a spectroscopy study that, despite the poor quality of the data, they managed to constrain the possible values of the orbital period and the mass function of this transient, which indicates that the black hole nature of the compact object. But what makes this object so challenging to observe? Well, it's not only that it is a faint system with a magnitude of 22.7 magnitudes in the R band, but it also presents an interloper. I mean a field star. An interloper is a field star that is near our target. Here, I present the field of view around our object, and we have some in the area where Kytra is located here, marked with the red arrow, and we can see an object to the south, which is the interloper. They are separated by a distance of only 0.64 arcsecond, and they present similar magnitudes, which means that high-quality photometric and spectroscopy data are required to resolve both objects. So we performed time-resolved photometry of Kaitra on 2019 using the DICAM camera at Cerro Tololo Observatory. We obtained 2 nights of data in the R and I band and carry out aperture photometry. I have to say that this image is the acquisition image in the spectroscopy run, but we were unable to resolve both objects in the DICAM photometry. That's why we center a fixed aperture on the transient and the interloper and remove the contaminating flux from the field star by using the magnitudes obtained with the previously photometric study. The resulting light curve are shown here. We present the light curve before and after removing the contaminating field star. And for comparison purposes, we also plot the 2 additional field stars that have similar brightness to both light curves. We can see that we detected modulation that is intrinsic to the object. This periodicity is less clear in the second night, perhaps for the presence of a large level of flickering activity occurring this night. In order to identify the orbital period, we computed a Lomes-Kargel periodogram. We can see a dominant peak here above the 99% white noise significant level, which is the horizontal dashed line. So we can establish the orbital period of Kaitra by 0.26 days. We attempted to model the R-band light curve to establish the orbital inclination of the system. However, we were unable to obtain reliable values due to the possible presence of flickering activity in the second night and because the amplitude is changing between the nights. So we were unable to obtain this parameter. So what we had to do next is to exploit the H-alpha emission line relations. In 2016, we obtained 2 nights of high-quality time-resolved spectroscopy for Kaitra with the Force 2 spectrograph at the BLT. We acquired 3 spectra per night, covering a small fraction of the orbit. However, the double peak H-alpha emission line was the only spectral feature in the revealed. No clear evidence for photospheric absorptions were seen. We didn't detect the companion star in this case. Here, just for comparison, I am showing our average H-alpha emission line, and this is the only single spectrum that it was in the literature, and we can see that they couldn't detect the double peak H-alpha emission line. So by employing the relations between the properties of the H-alpha emission line mentioned before, we established the radial velocity semi-amplitude of the donor star and the orbital inclination. Due to the poor orbital coverage, we adopt a 10% uncertainty to account for the intrinsic full half maximum variability typically observed in these X-ray transients for the first case, and for the orbital inclination, we consider the variability observed in the depth of the throw for the system with similar orbital periods as Kaitra. However, we couldn't constrain, in this case, the mass ratio of the system because, as I mentioned before, it requires measuring the double peak separation and the full width with high precision. But in this case, due to the limited number of spectra, the mass ratio value presents large uncertainties. So what we did was we estimate K2 and the orbital period, which yields a mass function of 3.2. Remember that this represents a lower limit to the mass of the compact object and is higher than the 3 solar mass limit, which we can say that there is a strong indication of a dynamical black hole. We also established the orbital inclination, and the only ingredient we have left was the mass ratio. But we can establish an upper limit on this parameter based on the color information in the R and the E bands from the DCAM photometry. After correcting from the interstellar reddening, we determine the reddened quiescent color of 0.27. This is consistent with a K2 spectral type companion star, but we adopt the most extreme case with the color. We find that the companion star must have a spectral type later than G8, which translates into having a mass ratio less than 0.31. So all these constraints yield the black hole and the companion star masses of Kytra, and our results confirm for the first time a black hole in this X-ray transient. On the other hand, we have the case of the X-ray transient XTE J1859+226, where the black hole nature was confirmed by previous studies during quiescence. However, the black hole mass had a large uncertainty due to bad measurement of the orbital inclination. For this object, we present 2 nights of simultaneous time-resolved spectroscopy and photometry. We obtain a spectra with the Osiris spectrograph mounted on the GTC. Unlike the spectrum of Kytra, here we are able to detect the companion star, which means that we can derive the radial velocity curve to obtain the sum of the fundamental parameters. Here I showed from bottom to top the spectra of a Chi-Phi spectral template and a K7, and this is the normalized spectrum of the X-ray transient. Although they are quite weak, we detected some metallic lines such as 6162 and 6495. By cross-correlating the individual spectrum with the spectral templates, we obtain the radial velocity semi-amplitude, and as an independent test, we derive the same parameter with the H-alpha emission line correlations, and we can see that these two quantities are fully consistent between each other, so we can combine them and obtain a more precise estimation. In addition to the radial velocity curve, we have fitted, this is the radial velocity curve, we have fitted a symmetric 2 Gaussian model to the double peak alpha emission line in the individual spectra to obtain the centroid velocity of the profile. Here it is shown. Both quantities are modulated by the orbital motion of the companion star, as we are seeing in here. By computing a Lomes-Kargel periodogram, we derive the orbital period of the system by considering the only 2 peaks that were above the 99% white noise significant level. Finally, we exploit again the empirical relation by fitting the single and a double Gaussian to the H-alpha emission line. I am sorry for repeating the same emission line every time, but we can see that this peak is very prominent with high signal to noise, which allow us to obtain a very precise orbital parameters. In this way, we establish the mass ratio and the orbital inclination of the system. Now we have all the ingredients to obtain the black hole mass. With this work, we updated the refined compact object mass, and the companion star mass is also consistent with its Chi-Phi 7 spectral type. These two systems are just 2 examples of the fast improvement we are making with these new relations. Here we present another 2 very faint X-ray transient with magnitudes between 23 and 24 in the R band. And by plotting this line, we have derived their mass functions. In the 2 system, this exceeded the maximum neutron star mass and therefore demonstrate the presence of black holes in these X-ray transients. So the faint X-ray transients are not hidden for us anymore, at least some of the system. This is the plot of the mass function for the 19 known dynamical X-ray binaries versus the R-band quiescent magnitudes. The 2 marked in red are based on radial velocities studies in the near infrared because they have They are located in a very reddening interstellar position. So they have to be studied in the near infrared. The vertical dashed line represents the maximum neutron star, and as we can see, classical radial velocities are limited down to 22, to a magnitude of 22. However, with these new techniques implying the H-alpha correlations, we go much deeper, 3 magnitudes deeper, and recover some of the historical quiescent X-ray transient that have been lost during quiescent. We expect to increase the census of dynamical black holes by 50%. We hope so. And these masses were made by spectroscopy studies, which they are difficult to carry out. So what we are investigating is a way to measure H-alpha width photometrically. We found that this can be optimally accomplished with 3 custom H-alpha filters. The 3 filters must be centered at the rest wavelength of the H-alpha line, with increasing width to cover the core of the line, the entire line flux, and the nearby continuum. Through synthetic simulations, we show that combining the fluxes measured with the 3 filters, it is possible to recover photometrically the input line width, so irrespectively of the equivalent width of the line. Therefore, the 5 filters define a new photometric system that is especially tailored to measure the width of the H-alpha lines. An easy way of presenting different H-alpha emitters population, like BE stars or X-ray transient, is using this color diagram. We have plotted here lines of constant equivalent width and constant full width of maximum, which are the vertical lines, the curved line. Most H-alpha emitters have narrow lines under the 1,000 kilometers per second and are easily segregated. However, the most important part of this diagram is that when we see a cutoff here at 2,200 kilometers per second, where there are here the 50% of the black hole population. This black hole must have also short orbital periods under 2 hours and will be eclipsing, which will make them easy to spot in 2 hours light curve, hopefully. So what we only need to do is looking at the sky for H-alpha width of more than 2,000 kilometers per second to detect black hole X-ray transients. To test this observing strategy with the goal of doing an all-sky surveys, we have signed the Mini-HAWKS project. This is a pathfinder that has been approved as a legacy survey for the JUST 80 telescope. They are at the Observatory of Alambre, and has been awarded 400 hours of observing time. The 3 filters have been already produced and delivered. We plan to start this summer observing, and we plan to survey 50 square degrees over the next 2 or 3 years. We expect Mini-HAWKS will deliver 2 or 3 new black holes, hopefully, but also several hundred of other H-alpha emitters like cataclysmic variables or BE stars, and so on. So stay alert for the incoming news. And I will end this, and I think my time has arrived, and I will end this talk. Just wanted to say that the best way, an easy way to measure black hole masses is through dynamical studies of X-ray binaries in our galaxy. Novel strategies such as H-alpha relations are needed to discover the black hole lost that they were lost during quiescent. Better statistics are required to derive constraint to close binary evolution and supernova models. Finally, these exciting projects such as Mini-HAWKS will put the seed to all sky surveys for searching new quiescent black hole X-ray transients. I want to thank you all for your attention, and especially Alessandro and Juan for inviting me here. And it was a really pleasure to be. I wish that I was there, but I will be happy to answer your question now.
Thank you very much, Idaira, for the talk.
Thank you.
Questions? Helios?
Thanks, Idaira. Very nice talk. Well, in the relation where you use the inclination angles to get spherical relation, is that only from ellipsoidal modulation?
This
Like,
one.
the systems that get like the ones on the plot on the right that Jorge has, all the values are on the left. Sorry, where you show the spectra and you have all the derived inclinations, right? Is that how is that measured? Is that from ellipsoidal modulation only?
It depends on the system. This inclination were obtained from the literature. Sometimes it comes from the from light curve modeling, but also they came also from X-ray model. It depends on the transient. But I think most of them came from light curve modeling.
Because I'm surprised at the very small error bars, and because in general, the lower the inclination, the harder it is, right? Like this X4, for example, 34 degrees inclination, that should have a large error bars. But in your plot, I would say this. I would expect this from an eclipsing system, perhaps, but they seem a bit small. So I was wondering how do they get these?
I know that we took them from literature, but I don't remember exactly how they were made in each case, so I am not sure.
And the second question, if I may ask?
So
none of them is eclipsing from the ones we know. We know of 70 of them, right? X-ray none of them is eclipsing, like a high inclination.
Some of them are eclipsing, but the problem is we are not. We know that they are eclipsing from the X-ray information, but photometrically in the optical, it is very hard to do these studies because they are too faint. So we are detecting light curve like this that we are not detecting so much ellipsoidal modulation or eclipsing. So it's difficult. But in X-ray, they are detecting eclipses.
More questions? I have one about the meaning of the K2H alpha relation is that the larger the amplitude of the companion star, the larger the fastest the disk rotates. Is that correct?
The larger the semi-amplitude, the fastest the disk rotate. Did you mean?
Yeah. Is that correct?
Yeah. You are correct.
The mechanism behind the correlation, right?
Yeah, you are correct. You're correct.
So the question is this relation extrapolable to other objects like neutron stars?
In this study, we are not using only X-ray transient, we are also using cataclysmic variables, and we have seen that this relation is very similar than for black holes. Yeah.
So in principle, in mini hawks in the survey, you're targeting black hole masses, but you might get also masses for many other systems, right?
Yeah. Here we are be able to obtain. We are going to observe a lot of H alpha emitters, and there are a lot of cataclysmic variables and other stars. So yeah.
Okay. And
we expect to obtain, hopefully, 100. I think it was like hundreds of cataclysmic variables.
So it's not only 2 or 3 black hole masses. Or
No. We are going to do a all sky surveys and detect all the H alpha emitters above the 1,500 kilometers per second and obtain all the H alpha emitters. But I am interested on the black holes, but we are going to observe a lot of these objects. Yeah.
Sure. After you have to classify those emitters and so on.
Yeah.
But in principle, you don't have to wait for the third black hole mass to be detected so you will have material to do science much earlier than that.
Exactly.
And the other question is about the plot, the black cat plot with the detections, the black hole candidates and measurements. What happened in the 80s with the discovery? In the 80s, the histogram is flat, so there was no satellite, or during that time, or.
I think that all the interested one or the easiest one was were studied, and that's why Jorge started to try to find a way to study those faint X-ray transients, because the problem is that most of them are very faint to observe, even with the 10 meters telescope. So I don't think that.
That's in the 2000s, but I'm asking about the discoveries, so the explosions in X-rays during the 80s.
Okay.
They're flat there. So that means that there was no X-ray satellite sensitive enough or rapid enough to trigger the observations or to detect them.
I am not sure. I don't know.
But something happened, no? Because they didn't stop exploding, I hope.
Yeah. I am not sure. Yeah.
Millennials were
millennials. Okay, more questions?
Just have a curiosity. What does the mini host stand for? What is the acronym?
H alpha is the
Okay.
K2.
Wave. I don't remember now. Sorry, I don't remember.
The parameter that people cover, no? It's the
H alpha
Width and
K. We have to talk with Jorge too.
Yeah.
Mainly because it's going to be a pilot survey, pilot study.
Yes, I think this started with a project for an ERC.
Whole sky.
That was it's a big thing, and they were required a demonstration. So that's when Jorge started to design a survey that proves that the methods work on a statistical basis. I don't know the full hoax, how large it's supposed to be. Is Jorge already thinking about that? Probably, no?
Yeah. I think he has all the procedures he is going to do with the full survey, but I don't have this information. So.
No reason why not to go whole sky. If it works.
Yeah.
You just book the T80 for the next 15 years, and it's.
And the sound. And
the Jota in just instead of Javalambre will be Jorge.
Okay, more questions? If not, thank you very much, Idaira, for this very
Thank you. Thank you very much.
Oh, you're dismissed. Bueno, voy a parar las grabaciones.
Perfecto.